Can you hear me? Thanks. Thanks for the introduction. So unlike the previous talks, this will be a talk about deterministic algorithm. Okay, so let's start with QColoring. So what is a proper QColoring? So say you are given a graph and you want to color the vertices with one of the Q colors, and you want to make sure that there are no monochromatic edges. So this is called a proper QColoring. So throughout the talk, I will let delta to denote to the maximum degree of the graph. And if we have at least delta plus 1 colors, then I guess everyone knows how to find a proper QColoring. So in fact, it can be found just by a greeting algorithm. But then a natural question would be, how many QColorings does the graph have? So this is a well-known number P complete problem. So we'll look for an approximate answer. So more precisely, we will be looking for a multiplicative approximation to the number of QColorings of this form. So 1 plus minus epsilon times the number of QColorings. So this approximate counting problem is known to be equivalent to many other algorithmic tasks. For example, there's the sampling question, which is you want to sample a QColoring uniformly at random. And the inference question, where you want to infer about the coloring, the probability distribution of the color of a vertex given some other boundary conditions. Okay, and many others. So here's our main result. So if there are 2 delta colors, then there's a deterministic algorithm to approximate the number of QColorings in time, polynomial in the size of the graph, and 1 over epsilon. So it works for any bounded degree graph. And for triangle-free graphs, we have a slightly better result. So we only need like 1.76 delta plus some constant, universal constant. And this works for any triangle-free graphs that are of bounded degree. Let me say a few remarks. So what is this 1.76? So this is closely related to something called the strong spatial mixing of least coloring. And it's defined by this equation. So it's the unique positive solution of this equation. Also, incomplete list of prior works. So for randomized algorithm, we know a slightly better result for this problem. So this started in an early work of Jerem. So by one-step coupling analysis of the global dynamics, he can show that 2 delta plus 1 is suffices. And actually, this 2 delta so this 2 actually corresponds to something known as the Partition condition for this problem. And by a comparison technique with a different Markov chain, so we go there, and more recently, by Chen et al., they can show something like 11 over 6 minus epsilon delta suffices. So this is slightly better than 2. But for deterministic algorithm, we are still nowhere close to that. So prior to our work, the best known deterministic algorithm is like still requires 2.58 delta. So for small degrees, there are some, if you really think about it, you can get all the way to the optimal result. So this is also by Ping and Lu. Okay. So let me say, so what's the technique that we use? So we will use a formal connection between algorithms and phase transition. So, and crucially in our work, we need to exploit both directions. So it's not just one direction. So what is this phase transition? So I guess many of you have seen like there are many problems that exhibit a computational phase transition. So as you vary some parameter of the problem can go from easy to become NP hard all of a sudden. So And in some of these problems, this transition point is known to coincide with some statistical physics define phase transition. So some of these examples include the hardcore model and the antiferromagnetic Ising model. Okay, so what is the phase transition in classical statistical physics? So roughly speaking, is defined to capture discontinuity of observables. So as you change some parameter of the system, you will see some observable, like a macroscopic observable, changes continuously initially. But when you lower the temperature of the system, this transition gets sharper, and then as you let the size of the system tends to infinity, it can become a discontinuity. So to say this more precisely, let me define what's called a partition function. So a closely related model to QColoring is what's known as the Potts model. So what's the Potts model? So given a graph, a configuration will be, so it assigns one of the QColors to all the vertices. But now we allow improper coloring as well. So sometimes there may be a monochromatic edge, but we will assign a weight W for each monochromatic edge. So the partition function will be so it enumerates over all not necessarily proper QColorings. And for each such coloring assignments, we give them a weight, W to the number of monochromatic edges. So let me just denote the set of monochromatic edges as E equals sigma. Okay, so for the Potts model, there are two important special cases. When W equals 0, okay, so this partition function is actually a polynomial in W, but the constant term, so when W equals 0, it actually corresponds to the number of QColorings. So this is like saying we are forbidding all monochromatic edges. And the Gibbs distribution will just be that we assign, so the probability that we get any configuration is proportional to the weight. So it's proportional to W to the number of monochromatic edges normalized by the partition function. And our goal will be to compute this partition function multiplicatively in a multiplicative approximation fashion. Okay, so now we can define the phase transition more formally. So this is a program started by Li and Yan. So they propose to study phase transition through the non-analyticity of what's called a free energy. So roughly speaking, they observed that the analyticity of the log of the partition function is roughly the same as the continuity of the observable. So why is that? So let's recall the partition function definition. And it turns out that like many macroscopic observables can be written as some quantity related to the derivative of the log of the partition function. So this is an example. So this is like, imagine that you sample a configuration according to the Gibbs distribution. Now, how many monochromatic edges do we expect to see? So this is like the average number of monochromatic edges. So this is a macroscopic observable. And if you write it out, you can see that this is exactly equals to, if we take the derivative of the log of the partition function with respect to W. So when you take the partial derivative, you first get the 1 over C factor. So this is gives you the probability. And when you use the chain rule, you see the extra factor. Okay. So what have we learned from this? So roughly speaking, in order to see a continuous observable, so in order for this quantity to be continuous, we need the right-hand side also to be continuous. In other words, if we would like the log of the partition function to be analytic, so this will be a continuous function in W. And therefore, okay, so a little bit of complex analysis will tell you that the log of a polynomial, so the logarithm is only non-analytic at 0. So it's analytic everywhere else. And therefore, in order to see any phase transition at all, you have to look at the point where the partition function vanishes. Okay, so is this intuition clear? Okay, so basically, this is just the intuition behind like why in statistical physics, lack of phase transition is characterized by lack of complex zeros. Okay, so let's move on to the first connection between algorithm and phase transition. So this connection has been explored in recent years in many of the works. So this is known as the Dominos Interpolation method. So given a partition function, and suppose that it's 0, 3 in some region, what Dominos interpolation method does is the following. So let's consider the Taylor expansion of the log C. Now, in a 0, 3 region, you can show that this Taylor series absolutely converges. And it can be approximated by the first k order of the Taylor series by just choosing this parameter k to be like log n over epsilon. And an additive approximation to the log of the partition function will translate to a multiplicative approximation to the partition function itself. And now, in order to compute the kth order Taylor series, you observe that it suffices to compute the k plus 1 coefficient of C, but obviously this is non-trivial in general. And naively computing the first k plus 1 coefficient can take order n to the k time. But let me just mention that if you exploit the combinatorial structure of the partition function, this can be you can speed this up to the time something like delta to the k. So this is the place where we use the fact that the graph is of bounded degree. So for constant delta to the k, where k is like log n, then this becomes a polynomial in n. Okay. So this is the first direction. Now, what about the second direction? So we've seen that if we can show a 0, 3 region of the partition function, then there's an algorithm for approximating the partition function. So where does this 0, 3 region come from? So we will study, so let's recall the partition function. So the zeros in W, so we are going to view this as a polynomial in W. So the zeros in W is known as the Fisher zeros. And it's notoriously difficult to study where the Fisher zeros are. And so crucial in our work is a new zero freeness result, establishing that when Q is at least 2 delta, then the partition function does not vanish in a rectangular strip containing the interval from 0 to 1. Okay. So prior to our work, the best known result still requires E times delta plus 1. Okay. And similarly, for triangle-free graphs, we show that when Q is at least 1.76 delta, then there's also a rectangular strip containing the interval 0 and 1 such that the partition function does not vanish. And based on this and the previous connection, the Dominos interpolation method, this implies an FP task for bounded degree graphs. Okay, so how do we show our zero freeness result? And it turns out that we are going to use a different algorithm. By analyzing a different algorithm, we are able to establish this zero freeness. And okay, so what is the main idea of this? So this is the partition function. So if so let's consider a case where W is in zero, is an actual real number on the 0-1 interval. In this case, we know that there's at least one QColoring as long as Q is at least delta plus 1, right? That means that the partition function, when W is a non-negative real number, because the constant term encodes the number of QColoring, so the partition function is at least 1 for real W. But now, when we consider W tilde on the complex plane, if we can somehow compare these two partition functions through an algorithm. So, okay, so suppose that there's an algorithm that on input W computes the partition function. Similarly, on input W tilde, output the partition function at W tilde, and we can compute, and we can compare the trajectory of the algorithm in some way, then we will be able to also conclude that when moving to the complex plane, the partition function does not vanish. So what is the algorithm we'll consider? So let's do actually one more step. So let's fix the vertex and consider the following restricted partition function. So what is C of I? So C of I is where we restrict to colorings where vertex V receiving color I. So for example, I is the green color, then we are going to pin the color at vertex V to be I, and just consider colorings of everything else. So in this way, we can write the partition function as summing over all possible color to V, and summing similarly for W tilde, we can write this out. And now let's pick any color J. In this way, we'll be able to write this as a product of a smaller, of a restricted partition function times a sum over these ratios. So suppose that we can control this two quantity. So suppose that we can control the restricted partition function through an induction, and moreover, these ratios, we can show that they are approximately equal. Then we will be in good shape. Okay, so how do we do that? So it turns out that there's a well-known tree recurrence for computing the ratios. So this ratio of two partition functions, roughly speaking, correspond to a marginal distribution of the Gibbs distribution. So essentially what we show is that regardless of the size of the graph, there's a, as long as you're comparing the ratio of the same color, so for the same color I and J, then moving to the complex plane doesn't change the marginal distribution too much. So and this change doesn't depend on the size of the graph. And to prove that, we basically treat the tree recurrence as a complex dynamical system, and but this is can be very challenging to analyze because not every orbit is well behaved unless Q is substantially greater than 2 delta, and this is actually the main barrier why all the previous work cannot get anywhere close to 2 delta. But the key idea in our work is to show that there's a high entropy orbit such that this complex dynamical system is well behaved. So Yeah, so basically we use a tree recurrence to study the ratios. And this tree recurrence, we are going to look at it as a complex dynamical system. And it's a little bit, so it's well known that there are not so well behaving orbits, so they can actually diverge because this, I mean, it can depend on the graph. And when you change like in general, they can be very sensitive to the input. But there exists a high entropy orbit such that they don't diverge when you change the parameter like that, just a little bit. And this high entropy condition is essentially captured by the fact that when you have enough colors, then the marginal distribution has high entropy. So yeah, so there's a conjecture that if you have high growth, then this high entropy condition will still be satisfied even with fewer colors. Okay, so I'm running a little bit out of time, so let me just quickly recap that we can exploit an analysis of algorithm, which is a tree recurrence, to prove that the marginal distribution, when you move it to the complex planes, it still remains roughly the same as the real value marginal distribution, and we use that to prove zero freeness. And conversely, it has been shown that zero freeness result can be exploited algorithmically. And using both connections, we conclude our new algorithms. Okay.